All right, let's get right into this. We're going to do a little bit of review on solving logarithm equations here, but there's a couple of strategies that I really want to point out to you. A couple things when you're solving a logarithmic equation, write this in red ink if you have red ink, but you should always check. Specifically, the thing that you're going to be checking for is if you end up with a negative answer, to plug that back into your x. I'll show you what I mean on this very first problem here, actually. So, a couple things we need to know. If we have a problem and we know that, like, say, log base a of b is the same thing as log base a of c, then doesn't that just mean that b and c are the same? And so we can make a new equation, doesn't even have any logs in it, saves us a lot of time. But, well, not but let's go ahead and use that then. So let's take a look at this problem. And the very first thing I notice is we got multiple logs here, but I have a plus. And a plus in between two logs is really like multiplying the things inside. So actually I could say, you know what, this is the same thing as log base 3 of, I'll use a bracket here, x times x plus 7 equals log base 3 of 60. And now, what do you know? Look, I have log base 3, so that means whatever's inside this log has to equal what's in this side, this log. So I could just go ahead and say, you know what? And I'll go ahead and distribute this left side. I could just say x squared plus 7x must equal 60. And right away, I'm recognizing, hey, that's a quadratic. So quadratics, we want to make them equal to 0. So let's convert that to x squared plus 7x minus 60 equals 0. And we could use a quadratic formula, or we could try to factor. I always try to factor first. I think it's easier to. So I need something multiplies up to 60, adds up to 7. I think I could do a 5 and a 12. I think the 5 would have to be negative. Remember about factoring, though, your factors are not your solutions. They're their opposites. So that means that your solutions would be negative 12 and positive 5. Now, let's check with that for just a second. We want to check for negatives. So let's plug in this negative 12 for x and see what we end up with. We end up with log base 3 of negative 12 plus log base 3 negative 12 plus 7 equals log base 3 of 60. And we're going to run into some problems with this solution. Specifically, let's just look at this first one, and I think you'll see why. I want you to pretend like I wrote log base 3 of negative 12 equals, let's just say y. And if I rewrote this in exponent form, it would be 3 to the y equals negative 12. Well, if you think of this as a function, this function never becomes negative. It just increases forever. You could put in a really big negative number here, like negative 1,000,000, but really that would just be really close to 0. It would still be positive. And if you put in a really big positive number, you're just going to get a giant positive number. So this actually can never happen. And since this can never happen, this whole thing just can't work because we cannot have we can't have negatives inside of any log. It's just not possible to do. So this is going to end up with a negative 5, so this won't work. So that means that negative 12 is not a possible solution. That's okay, though. Let's try the other one. Let's try log base 3 of 5 plus log base 3 of 5 plus 7 and log base 3 of 60. Does that equal? So we end up with log base 3 of 5 plus log base 3 of 12 equals log base 3 of 60. And that checks out because we know from our log rules that a plus out here is multiplying on the inside, and 5 times 12 is in fact 60. So we're good. But you could also go to a calculator, you could type this in, then you could say plus, type this in, and you would get exactly the same thing as this. So we got it. We got a working answer here. So that's why you always want to check. You're mainly checking for negatives inside the log. You can have a negative, but like, for example, let's say this is negative 5. That's okay because negative 5 plus 7 still makes it 2. So that would work out. But if I get a negative, if this whole thing ends up being negative, it's not going to work. All right. Let's try another one here. Let's see if there's another way some other strategies we can for solving something like this. So I got constants and logs mixed together. A little bit tricky. But what we can do here is we could just get all the logs on one side. So I'm going to add all of this to both sides. I know I'm being lazy and just putting quotation marks, but let's see. What would that end up? I'd have log base 2 of 5 plus now log base 2 of x plus 7. And again, now I have this plus sign, which means that this is really like multiplying. So I could say this is really like saying log base 2 of 5 times x plus 7. And we could just go ahead and distribute that, make our lives a little bit easier. So that's going to be 5x plus 35. Well, now what we have is just a general log equation, and we could just convert this to an exponential one. So if I convert this to an exponential, it would be 2 to the third equals 5x plus 35. That really is an 8. And so now I'm going to just subtract 35. And it's a pretty easy equation to solve now. So that's negative 27 equals 5x. Divide by 5, divide by 5. And we got an answer, but it's a negative answer, so let's just think about this. So x is, what would that be? That's negative 5 and 2/5, so 5.4. Well, that's going to be okay, because if I plug in a negative 5.4 here, I still get a positive value in my log. So this is going to be a valid solution. We're good. All right, so let's go on to another problem here. What about something like this? Okay, well, obviously the first thing we want to do is we don't really want this 3 here, so we're going to divide both sides by 3. So I get 2x plus 2 equals 4. Okay, a couple of things here I just want to point out. There is actually lots of ways to solve this one right here. We could do a lot of different things. When you can rewrite an exponential equation with the same base, I would do it that way. But I want to show you a few techniques here. So the first way I would try is, let's write the common base technique. But that won't always work. But in this one it will, because think about it. I could rewrite this as 2 to the x plus 2 equals 2 squared, and bam. This is going to be an easy problem, because if these two bases are the same, then these two exponents are the same. So I can just say x plus 2 equals 2, subtract 2 from both sides, and I get x equals 0. That's beautiful. But the intent of this problem is actually show you a couple other things that we could do. So another thing we could do is we could just write this whole expression right here as a log. So it's an exponent form, so I could say, hey, this is the same thing as log base 2 of 4, and that equals x plus 2. And then kind of another little technique that you could do is you could actually rewrite this now, kind of the same idea, but we could rewrite this as the same base if we wanted to, because I could say log base 2 of 2 squared equals x plus 2. And then remember, I can take this 2 here and I can move it out front. So I can think of it like this. And it turns out that anytime you have a base in this being the same, that's just a 1. So this whole thing just becomes 1. So this is like saying 2 times 1 equals x plus 2. Now I know that's a longer way around, but I just think it's important that you know this feature, that if you have the same base and the same thing in the log, your answer is just going to equal 1. And from here, you can see we get the same equation here, x plus 2 equals 2, and so we get the same solution. Obviously, that's a little bit longer way to do it, but I really want you to, the whole point of this problem was just for you to know this thing right here. Okay, let's keep going. Got another example here. On this one, we're going to use technology, and I'm actually going to have you guys pause the video. You guys know how to do this. We've done this in class. What you're going to do is you're going to make this your y1 and this your y2. And then you're going to graph these things. So you're going to say in your calculator, you're going to write this log x plus 6 plus 3, and then y2, you could just say equals 2. And even if this was a nastier problem, you could just still put it here. And then you're going to graph it, and you're going to make sure that you can actually see the intersection on your graph. So maybe you have to zoom out or change the window settings or something. But once you do that, you're going to hit, it goes second, calc, and then it's the 5th option down for intersect. And you guys have done this before. You're going to select your first curve, you're going to select your second curve, and then you're going to guess. You might have to zoom in on the where you think the intersection here is from the standard window, because it's not so obvious at first. And then when you do that, I end up with this as a solution. I get x equals negative 5.9. All All right, if you don't get the same thing, please talk to me in class about this one, but you guys have done this enough times. I think you guys get the gist on this one. All right, I want you guys to try some of these on your own. They are definitely challenging, but think about your rules and think about what you can do. You might not even have to use logs on all of them, but you can. But go ahead and just give it a shot and then unpause the video when you're ready to check back with me to see what you got. Okay, so I'm going to go over each one of these one at a time and just show you my way of doing it. There might be another way to do it. I try to avoid using a calculator just so I could practice my skills. If it's a calculator problem, I mean, if you're allowed to use a calculator, go ahead, just do this as y1, do this as y2, and you'll probably have a solution really, really quickly. But let's say you couldn't have a calculator on this for some reason. So let's think about how we could rewrite this. Well, I remember that the square root is really a 1/2 exponent, and I can put exponents out front. So I'm going to rewrite this. I'm going to write this as 1/2 ln x minus 12 equals 4. And I'm going to get rid of that 1/2 by multiplying both sides by 2. So now I have ln x minus 12 equals 8. And ln really just means it's a base of e. So now if I rewrote this in exponential form, it would be e to the 8 equals x minus 12. And hey, this is working out pretty easily. All I got to do is add 12 to both sides. And I have e to the 8 plus 12 equals x. Now, I can't get any more specific than that without a calculator, but that's a fine answer. That's exact terms. We like exact terms, so that's totally fine. But if you wanted to plug that in a calculator, get a decimal, you're more than welcome to, but not really necessary. All right, let's take a look at this one. So as I look at this one, the first thing that I notice is I got a lot of multiples of 3. Like 9 is 3 squared, that's 3 cubed, that's 3 to the 4th. So I think we can use something like getting common bases here, and I don't think we even have to mess around with logs. First things first, though, let's get rid of this 9 hanging out front. That doesn't do me any good. So I got 1 over 27 to the x third equals 9. And I'm going to try to rewrite both of these as a base 3, and that's pretty easy. So 27 is 3 cubed. Oops. It's 3 cubed. So what I can do is I can think of this as 3 to the negative 3 since it's on the bottom. Right, so negative exponents just flip, and this is 3 squared. Okay, so now we're getting somewhere with these common bases. I think we can handle this pretty easily. From here, when you have an exponent to an exponent, you just multiply. Well, if I multiply this on top, my 3's will cancel out, and I'll just have a negative x. So this becomes 3 to the negative x equals 3 to the 2. And yeah, if I have the same base, the exponents must be the same. Therefore, we could just go ahead and say negative x has to equal 2, and therefore x equals negative 2. So easy peasy. You can plug it back in if you want to check your work. Make sure that you did it right. But that one's not so bad if you just use common bases. All right, let's take a look at one more. We got a lot going on here. We got all these different logs. Luckily, they're common logs. So we could do the same thing we did before. When we see a plus sign, that really means multiply. So let's rewrite this as log. I'm going to write the 3 first, just because it looks better that way. All right, well, let's go ahead and distribute the 3 and rewrite it. So we would get 6x plus 21 equals common log of x plus 6. Well, that's pretty easy. They're both the exact same log. They're both common logs. So we could just say, therefore, the inside equals the inside. So let's just change it to a normal equation. And let's just go back to algebra 1. Subtract the x, subtract the x, subtract 21, subtract 21. What would I have? Let's see, these would cancel, these would cancel. I'm going to have 5x equals negative 15. Divide by 5. That means x equals negative 3. Oh, no. What does that mean? I have a negative. Is that going to be a problem? Well, let's plug it back in and see. So if I go to the original, I'd have log 2 parentheses negative 3 plus 7. Oops, bracket. Plus log 3 equals log negative 3 plus 6. All right, so over here, that's negative 6 plus 7. That makes a 1. So this whole thing just ends up being log of 1 plus log of 3 equals log of 3. Now, at first glance, you might be like, how does 1 plus 3 equal 3? But remember, this really is multiplying. So this is really like saying 1 times 3 equals 3. And another interesting thing to know is if you got a log of 1, that's actually 0. And let's talk about why. I want to make sure you understand why. So just again, let's do that little trick, right? Just say, okay, let's say log of 1 equals y. Well, this really means base 10. And so if I write in exponent format, that means 10 to what power equals 1? Well, we should know that 10 to the 0 power gives us a 1. Same thing works if it's an ln. Let's just say it's ln of 1 equals y. Well, there's really a base e. So we could rewrite this as e to the y equals 1. And the only way to get a 1 from any number, just changing the exponent, is just make the exponent 0. And so that's how we know that this log right here is a 0. And when you think of it in terms of a 0, now it makes a little more sense. This is 0 plus log 3 equals log 3. Or you could do the multiplication thing. 1 times 3 is 3. So there you go. See you guys on the next video.